Imagine a computer so fast that it could solve problems in minutes. These problems would take even the most powerful supercomputers on Earth thousands of years to compute. This is not science fiction. This is the promise of quantum computing. In 2019, Google made a stunning announcement. They claim to have achieved quantum supremacy. What does this mean? Google's quantum computer Sycamore performed a specific task in just 200 seconds. A classical supercomputer would have taken 10,000 years to complete the same task. This breakthrough marked a pivotal moment in the history of computing. We are now on the cusp of a new era. This is the era of quantum computing. This revolution is not just about speed. Quantum computers utilize the bizarre laws of quantum mechanics. These laws govern the behavior of particles at the atomic and subatomic levels. This allows them to tackle problems that are impossible for classical computers to solve. The implications are far-reaching, touching fields like medicine, materials science, and artificial intelligence. But this new technology also presents potential risks, particularly to our current cybersecurity infrastructure. To understand quantum computing, we must first journey into the strange world of quantum mechanics. This is the realm of atoms and photons where the classical laws of physics we experience in our everyday lives break down. In the quantum realm, particles can exist in multiple states at once, a phenomenon known as superposition. Imagine a coin spinning in the air, neither heads nor tails but existing in both states simultaneously. This is how particles behave in the quantum world. Another bizarre concept is entanglement. This is where two particles become linked. They share the same fate, no matter how far apart they are. Think of two coins flipping in perfect unison, always landing on the same side. Even if they are miles apart, their fates are intertwined. These strange and counterintuitive phenomena are the very principles that quantum computers harness. Quantum mechanics might seem like a mind-bending abstraction. However, it underpins many technologies we rely on today. Lasers, transistors, and even medical imaging techniques like MRI all rely on the principles of quantum mechanics. Quantum computing takes these principles a step further, manipulating the very fabric of reality to perform computations in ways never before imagined. At the heart of a quantum computer lies the qubit. Qubits are the quantum equivalent of bits, the zeros and ones that classical computers use to represent information. A classical bit can only be either a 0 or a 1. A qubit, however, can exist in a superposition of both states simultaneously. This unique property allows quantum computers to perform computations on multiple possible values at the same time. This vastly increases their computational power for certain types of problems. Imagine you have a maze to solve. A classical computer would have to try each path one at a time until it found the exit. A quantum computer, on the other hand, could explore all paths simultaneously. This is because of the superposition of the qubits. This parallel processing allows quantum computers to find the solution much faster. However, building and controlling qubits is a formidable challenge. Qubits are extremely fragile and susceptible to environmental noise such as vibrations and temperature fluctuations. These disturbances can cause errors in the computation. Scientists are working tirelessly to develop more stable qubits and error correction techniques. This is essential to unlock the full potential of quantum computing. In 2019, Google's Sycamore processor, a 53-qubit quantum computer, made headlines by achieving quantum supremacy. This milestone demonstrated that a quantum computer could outperform even the most powerful classical supercomputers for a specific task. The task involved verifying the output of a random quantum circuit. This may seem like an obscure problem. However, it has significant implications for the future of computing. Sycamore completed the task in just 200 seconds. Simulating the same task on a classical supercomputer would have taken an estimated 10,000 years. This dramatic speedup showcased the potential of quantum computing to revolutionize fields such as cryptography, materials science, and drug discovery. Google's achievement was a major step forward in the field of quantum computing. It proved that quantum computers could indeed solve problems beyond the reach of classical computers. This breakthrough sparked a wave of investment and research in quantum technologies worldwide. Section 5. Quantum supremacy. What does it really mean? The term quantum supremacy has sparked both excitement and debate within the scientific community. Some argue that it overhypes the current state of quantum computing. They point out that the tasks where quantum computers excel are still quite specialized. These tasks may not have immediate practical applications. While it is true that we are still in the early days of quantum computing, the achievement of quantum supremacy should not be underestimated. It is a crucial milestone. This demonstrates that quantum computers can outperform classical computers. This paves the way for future breakthroughs with real-world impact. The development of quantum computers is a marathon, not a sprint. There will be many challenges to overcome and milestones to achieve. However, the promise of quantum computing is too great to ignore. It has the potential to revolutionize numerous industries and address some of humanity's most pressing challenges. Section 6. The promise of quantum computing, a brighter future. The potential applications of quantum computing are vast and varied. One of the most promising areas is drug discovery. Quantum computers could simulate the behavior of molecules with unprecedented accuracy. This would accelerate the development of new drugs and therapies for diseases like cancer and Alzheimer's. Another area where quantum computing could have a profound impact is materials science. By simulating the behavior of materials at the atomic level, scientists could design new materials with superior properties. These materials could revolutionize industries from aerospace to electronics. Quantum computers could also revolutionize artificial intelligence. They could power machine learning algorithms that are exponentially faster and more powerful than anything possible today. This could lead to breakthroughs in fields like image recognition, natural language processing, and self-driving cars. The potential benefits of quantum computing are not limited to scientific advancements. They could also have a profound impact on our daily lives. Imagine a world where traffic flows smoothly. This would be possible because of quantum-powered optimization algorithms. Imagine personalized medicine tailored to your unique genetic makeup. These are just a few examples of how quantum computing could shape the future. Section 7. The dark side of quantum. A threat to cybersecurity? While quantum computing holds immense promise, it also poses potential risks. One of the most significant concerns is the threat to cybersecurity. Most of today's encryption algorithms rely on the difficulty of factoring large numbers. This is a task that is practically impossible for classical computers to perform in a reasonable time frame. However, quantum computers excel at factoring numbers. This is due to their unique ability to explore multiple possibilities simultaneously. This means that a sufficiently powerful quantum computer could potentially break the encryption that protects our online transactions, confidential data, and critical infrastructure. This threat is not immediate. Large-scale, fault-tolerant quantum computers capable of breaking current encryption are still some years away. However, the potential consequences of such a breach are so significant that we must start preparing now. Section 8. Quantum-proof encryption preparing for the future. The good news is that researchers are already working on developing quantum-proof encryption algorithms. These algorithms are designed to be resistant to attacks from both classical and quantum computers. One promising approach is lattice-based cryptography. This involves encoding data within complex mathematical lattices that are difficult for even quantum computers to solve. Another approach is to use quantum mechanics itself to create unbreakable encryption keys. Quantum key distribution, or QKD, leverages the principles of quantum mechanics to ensure that any attempt to eavesdrop on a communication channel is immediately detectable. Transitioning to quantum-proof encryption will be a complex and challenging undertaking. It will require collaboration between governments, industry, and the research community. However, it is essential to ensure that our data and communications remain secure in the quantum era. Section 9. Quantum computing for everyone. A distant reality? When will quantum computers be as commonplace as the smartphones in our pockets? The answer is, not for a while. Building and maintaining quantum computers is an incredibly complex and expensive endeavor. Qubits are extremely fragile. They require highly specialized equipment and expertise to operate. However, this does not mean that quantum computing will remain confined to research labs forever. Cloud-based quantum computing platforms are already emerging. These platforms allow researchers and companies to access quantum computers remotely. This will democratize access to this transformative technology. As quantum computing technology matures and costs decrease, we can expect to see more widespread adoption. In the future, quantum computers could be used to design life-saving drugs, create new materials with extraordinary properties, and power artificial